We will be doing a problem on design of beams. Okay, so let us take a problem. Okay, so the beam is of 5 meter span. Then it is having lateral restraint. It is having lateral restraint, and then the lateral restraint is in the top compression flange. Okay, and there is a uniformly distributed load. Okay, UDL, which is of 20 kilonewton per meter. Okay, and actually 20 kilonewton per meter dead load is there. Okay, and 20 kilonewton per meter live load is also there. Okay, so this is the loading. Okay, and then we have to take fe 410 grade steel. Okay, so if we draw the diagram, okay, how will it look like? So let us draw it. So this is the simply supported beam. So this is 20 kilonewton per meter dead load plus 20 kilonewton per meter live load. Okay, so the span is of 5 meter. Okay, now we have to design this beam. Okay, we have to do the design. Now when I talk about design, we have to take factored load. We have to take factored load. So let us factor it. We take factor of 1.5, then you multiply 20 plus 20 dead load plus live load. Okay, so ultimately it becomes 60 kilonewton per meter. Okay, so if the load is total 60, then what will be the bending moment? Okay, if W is 60 and 60 kilonewton per meter, length is equal to 5 meter. So the maximum bending moment will be maximum bending moment is equal to WL square by 8. So what will be the value of WL square by 8? It will be M equal to 60 into 5 square by 8, which is equal to 187.5 kilonewton meter. Okay, so from moment we have to find out the section modulus required. Okay, ZP required. So ZP, the formula is ZP required. The formula is m into m naught by fy. Okay, so it will be 187.5. If I keep it in mm, okay, into 10 to the power 6 into 1.1 by 250, which is equal to 825 into 10 cube mm cube. Okay, so in this way we have got the section modulus required. So after the section modulus is obtained, we will try to provide a section, and in such a way that the section will have a section modulus greater than the section modulus required. So select a section having greater value of ZP. Okay, so if you look into IS 800 on the backside, like page 138, the tables are given. So from these tables, you'll see that for various I sections, since we will be using I sections for beam. Okay, so we'll be using I sections. So we'll be seeing that for various I sections, various values of ZP are there. So let us try an I section whose ZP is greater than the ZP required, which is 825 into 10 cube mm cube. So from the table in on the back side, from page number 138 onwards, we see that if we take ISLB 350 at 0.486 kilonewton per meter. Okay, if we take ISLB 350 at 0.486 kilonewton per meter, see this 0.486, it's sometimes given in the form of kg per meter, so you have to just convert it into kilonewton per meter. Kg convert to newton, then convert to kilonewton. Okay, so that is just a conversion it is given here. So uh, that is the thing. Okay, no need to get confused. Okay, it is just the conversion of kg per meter, 0.486. So if we select this one, ISLB 350, let us write down the properties. So let us draw it. ISLB 350. Okay, so let us write down the values. H is equal to 350 mm, B equal to 165 mm, then thickness of flange equal to 11.4 mm, then depth of web depth of web. Okay, see, for depth of web, if you look into the web, a little closely. You see, this is the part where the flange starts, right? This is the part where the flange starts on both sides. Now, when the flange gets converted to web, this is the flange, this is the web. When the flange gets converted to web, at first it takes a curved portion. Okay, this is the curved portion, and then only after a little bit like this, from here to here only, the web is of constant thickness. So we will consider the web, okay, the part having constant thickness. We'll consider the part having constant thickness. So this part will not will be what? If you look at it here, if this is the part having the constant thickness, and remaining like these are what? These are the curved parts. So we have to subtract these curved parts also. Okay, so that curved part is nothing but the radius of the root. Okay, that is termed as r, and which is equal to 16 in this case. Okay, so this part is 16. This part is also 16, and flange we know 11.4. Okay, so when we have to find out the depth of the web, the total depth is how much? We have already known it is 350, right? So from 350 we have to subtract obviously the flange on both sides and also the root on both sides. Okay, so what will be the final value? 295.2 mm. That means we consider the depth. Okay, this is the depth. Okay, of the web having of the web of the part having constant thickness. Okay, so 295.2. Now thickness of web is TW, okay, which will be 7.4 mm. TW is equal to 7.4 mm. Okay, now for the section ISLB 350, the IZZ is equal to 13200 into 10 to the power 4 mm4. Okay, then elastic section modulus, there are two section modulus, one is elastic section modulus, one is plastic section modulus. Let us write down both. For the section ISLB 350, 751.9 into 10 cube mm cube, then here it is 851.11 into 10 cube mm cube. Okay, which is we are comparing this plastic section modulus, okay, and which is greater than ZP required. Okay, so our part is done. All right, we always go with the plastic section modulus, because you see we try to achieve a load. You see, plastic section modulus is related to what? Plastic moment. Okay, and elastic section modulus will be obviously related to a moment which is of lesser value, moment of less value, and we try to give the loading in such a way that it at least tries to reach the plastic moment. Otherwise, what will happen? The full capacity of the beam will not be utilized. Okay, if you don't give the loading till plastic moment. Okay, and if suppose this one is just for example 500 kilonewton meter, and this one is 300 kilonewton meter. If we restrict the loading till 300, then the full capacity will not be utilized. But so to utilize the full capacity, we have to try to give a loading till 500. Okay, that's why we consider till this MP. Okay, higher moment, and that's why we are dealing with this. And this MP is what the load is. You see, the load that is given to us is how much? The MP that is given to us is MP. Actually, this fellow 187.5 kilonewton meter. The applied moment is generally considered as plastic moment, because this is the ultimate point. Okay, MP. Okay, so we always consider till the plastic point. Okay, we don't restrict ourselves to a lesser value. All right, so now let us do the classification of the section. So section classification. Okay, so for that we need actually two values, which is uh, b by tf, okay, and d by tw. Okay, b by tf and d by tw. Now if you look into the diagram, this b is half of width of flange. Okay, this is not this full width. Okay, so always keep that in mind. All right, so it will be how much? If we consider it as the half of width of flange, it will be 165 by 2 by tf. Tf is 11.4, so we get it as 7.23. Okay, and d by tw, d is the depth of the web. Okay, through the part having constant width. Okay, so 295.2, after like subtracting both the root and the flange, okay, divided by 7.4, we get 39.9. Okay, now if we look into the IS code, okay, if we look into the IS code, there is a table. Okay, so in that table, there it is in page number 18. Page 18, table 2. So first of all, let us consider the value of b by tf. Okay, before that, let us also take into consideration one term which is known as epsilon, which is 250 by fy. Now for fe, 410 Fy is 250. So epsilon is 1. That you should keep in mind. Okay, now this formula epsilon is equal to 50 by Fy, it is already there in given in page 18 table 2 notes number 2. Okay, it is given note 2 on the bottom. So let us first take into account the value of b by tf. Okay, b by tf. So b by tf we have got 7.23. So our section is a rolled section. Our section is a rolled section. So you have to go to the part having the roll section. Okay, it's there at the very top. Okay, of the table 2, page 18. I'm repeating it once again. Now, for there are three classifications: class 1, class 2, class 3, plastic, compact, semi-compact. So class 1 it is written 9.4 epsilon. Okay, that is 9.4 only because epsilon is 1. Okay, and class 2 10.5 and class 3 15.7. Now see, if your value is less than or equal to 9.4, less than or equal to 9.4, it will be class 1. So it is what, less than 9.4? So we can say it is class 1. But if your value is between 9.4 and 10.4, that means it can be 9.6 also, it can be 10 also, but up to 10.5, then it will fall under class 2. Again, if your value is between 10.5 and 15.7, like 10.6, 11, 13, 14, like that, then up to 15.7 it will be class 3. So according to this rule, now we have got it as class 1. Okay, now let us go to d by tw. D by tw, our d by tw value is 39.9. Okay, so for that you have to see the go a little down. Okay, you will see a point where it is written web of an I section. Okay, web of an I section. Okay, I H or box section is written, so we are dealing with I. So web of an I section. The neutral axis at mid depth. Our is an I section, isn't it? So our neutral axis will also always be at mid depth because it is symmetrical. Okay, so since it is at mid depth, neutral axis, so now we will be considering three values. Okay, for d by tw, for class 1, class 2, class 3. Okay, there are three values which are 84. Epsilon I am directly taking as 1. Okay, one is 105 and another is 126. So if your value is less than or equal to 84, it is class 1. So it is less than or equal to 84. Now it is ultimately class 1. But if your value is within 84 to 105, like 86, 90, 102 up to 105, it is class 2. And then if your value is like 106, 10, 115, 120 up to 126, it will be class 3. Okay, so that is the concept of classification. Okay, now let us go to the next step, that is the adequacy. Adequacy of the section including self-weight. Including self-weight. Okay, now see, the self-weight was not considered at the very beginning, isn't it? Because you see, we did not have any section at the very beginning. We are just given the load. Okay, we are told that there is 20 kilonewton per meter dead load and 20 kilonewton per meter live load. Okay, we were not told about any other load. Okay, and after there is no other load, okay, except these two. And after we had no section also till that time. So after deciding the section there is an additional self weight which we got along with it, isn't it? Additional self weight came, self weight, because at the very beginning there was no section, so no self weight. But after deciding that we will select IS LB350, there is a self weight which is coming into play, isn't it? So we have to take in account the self weight also now, along with the load that was previously there. Okay, so what will be the value of the self weight? The self weight was like a UDL, right? This is the beam and this is the UDL, this is the self weight, and we have to also factor it. So it is what? 0.486 kilonewton per meter, right? So it will ultimately be equal to self weight equal to 0.73 kilonewton per meter. Okay, so we have to take that into account. So final load, okay, final load is equal to what? Initially it was 60 kilonewton per meter plus this one 0.73 kilonewton per meter. So ultimately it is 60.73 kilonewton per meter. And the bending moment, okay, now the bending moment will change, isn't it? So maximum bending moment previously it was 187.5, isn't it? But when the load increased by 0.73, okay, so it will be what? 60.73 into 5 square by WL square by 8, isn't it? So you will get 190, okay, almost 190 kilonewton per kilonewton meter, 190 kilonewton meter bending moment. Okay, so that is the maximum bending moment that is actually acting. So for this maximum bending moment, okay, that is the actual, okay, actual moment that is acting, okay, actual bending moment. It is equal to 90 kilonewton meter. So it was not actually 187.5, it is actually 190. So for 190, again, what will be the plastic section modulus required? So it will be equal to, first of all we got one plastic section modulus for 187.5. okay, now for this what will be the required value? So keep it in mm, okay, 10 to 10 to the power 6 newton mm into 1.1 by 250. So ultimately we get 836 into 10 cube mm cube. Okay, that is the new plastic section modulus required. Okay, and what did we provide? what did we have provide? What did we have provide? The provided value of ZP was like for IS LB 350, the ZP was 851.11 into 10 to the power 3 mm cube, and it is greater than the new value. So our section is safe. Okay, if even after adding self weight, right? Without self weight, we got one ZP value. Okay, without self weight, we have got one ZP value, which was 825 into 10 cube. Okay, and after adding self weight, we got that actually the ZP required is not 825 into 10 cube cube. It is actually 836 into 10 cube cube after considering self weight. And the section that we provided is having a section modulus which is even greater than 836 into 10 cube cube. So in that case also our section is safe. Okay, so we have found out that our section is safe even if we consider self weight. Now after this step, what we will do is we'll be checking for shear force. Okay, we'll be checking the section for shear force. Then we'll be checking whether we'll be checking for safety against shear force and moment and deflection. Okay, so that we will be doing in the next class. Okay, so okay, so thank you.